Let me pull it up. Okay. Let's see. Okay, make it full screen. Okay, so here's your homework from last week. So you can go ahead and like pull up your copy or whatever if you want to check over your answers. I'll give you like a few seconds to do that before we start talking about it. Actually, first off, were there any questions on the homework? If I can pull up the chat. Okay. Okay, if there were no questions, then I will just start talking about the answers. So the answer to the first question was, well, it was the image I had on, I think, like one of the first slides. But cells would be the most basic. So the order is 3, 1, 4, 2. Okay, moving on, name two differences between plant cells and animal cells. You could have put any of the following: central vacuole cell wall, chloroplast. Did anybody put anything aside from these? Or did everybody put like two of the three choices that I have? Okay, yeah, so probably just what I've got here. Oh, basic to most complex. Most basic, so shouldn't the numbers be reversed? Let me double check what I have. The most complex, I mean like how it builds on each other. So cells would be the smallest. Cells form together to make tissues. Tissues form to make organs, and organs form to make systems. Does that kind of answer your question? I think the instructions might not have been super clear, but cells, tissues, organs, systems. Cells, tissues. Oh yeah, we did the same thing. That's exactly what I've got on here. By 1 to 4, I meant cells would come first, so that's why it's 1 here. Then tissues come second, so 2. Organs come 3, and then systems come 4. Does that make sense? Okay, no worries. So for number 3, the most unstable bond in the ATP molecule would be the third bond, the one between this P and this O, because that's the bond that breaks to release the energy and cause ATP to turn into ADP. Okay, on to water. Water is a universal solvent. Describe what that means. So a solvent is a substance that can dissolve another substance, which is a solute. So as a universal solvent, water dissolves a great number of solutes. That's kind of straightforward. But the point of that is so that you remember water dissolves a lot of things, and that's what makes it exceptionally important to life. Okay, rank the 3 bonds or attractive forces found in water from least to greatest in strength. So the weakest bonds would be London dispersion forces, which aren't really bonds, they're more attractive forces. Then we have hydrogen bonds, which is same case as LDS. They're more of attractive forces. And then finally, we have polar covalent bonds. Okay. 3, the difference between cohesion and adhesion. Cohesion is where like molecules stick together, so water on water. Adhesion would be unlike molecules stick together. One way you can think about this is if you think of like adhesive band-aids, how they stick to your skin. So that's like band-aid on your skin, which is 2 different substances, 2 different things. Yeah. Okay, and for pH, So a high concentration of H plus ions is a low pH, and a high concentration of OH minus ions is a high pH. That is because H plus ions make a substance acidic, whereas OH minus ions make a substance basic. Okay. What is considered a neutral pH? And give an example. So a neutral pH is 7.0. Pure water is the most neutral liquid because there are no ions present within water. And 3 environmental conditions that can impact an organism's ability to survive. You could have picked any 3 of pH, temperature, light, sound, or if you put something else, then something else, as long as it kind of checks out. Okay. Any questions? Okay, then I'm going to go to the presentation for today. So today we're going to be talking about energy. This is just kind of a basic overview of energy. Chances are you learned some of this before, and then some of it you didn't learn before. It's like kind of a nice mix between biology, chemistry, and there's a bit of physics in here as well. But yeah. Okay, can everybody see my screen? Okay, great. I'm gonna try and fix these things that show up. Okay, great. So let's get started. Energy, the force behind everything. So this is kind of like an overview of energy. This is going to be like more of the physics aspect, I guess. So you have a lot of different types of energy. It comes in different forms. There's mechanical energy, thermal energy, nuclear energy. I'm not going to read all of these out loud. But I'm pretty sure for every category, you can think of a way that you would find or see energy in that category. For example, let's take, some of these are a little bit weird. I feel like you could group these differently. But for example, ionization energy, that's kind of what we were talking about with ATP. That's the energy that ATP would release when you break that bond. But yeah, let's keep going. So there are 2 main types of energies that you will learn in like a basic physics class. You'll learn it in like chemistry. You might not go into too much detail in biology, but these are the ones that would show up. So you have kinetic energy and potential energy. Kinetic energy is the energy of motion, and it is dependent on the speed and the mass of an object. Potential energy is stored energy. It's kind of like the energy in position. It's dependent on distance from the source and the mass. So mass is very straightforward, but distance from the source. There is a type of potential energy called gravitational potential energy, and it's probably the most common. You're going to see it on your homework. But sorry, if I give you a question about potential energy on your homework, it's going to refer to gravitational potential energy. But gravity comes from the core of the Earth, the very center of the Earth. And so if you think about the source would be that center of the Earth. That is the source of gravitational potential energy. So the further you are from the core of the Earth, from the Earth itself, I guess in this case, the greater your potential energy would be. So if you have a certain understanding of math, you'll know exactly how kinetic energy and potential energy are dependent on speed, mass, and in this case, h refers to height or distance from the source. So first looking at kinetic energy, as the mass of the object increases, the kinetic energy increases, and as the velocity of the object increases, the kinetic energy will also increase. If we look at potential energy, this is specifically the equation for gravitational potential energy. As mass increases, your potential energy will increase. And as your height, this would be the distance from the ground in this case, increases, your potential energy would increase. The variable we didn't talk about was g. G stands for gravity. It's like the gravitational constant. and you would learn that in any physics class. You might not talk about it in a chemistry class. It depends. But yeah. So here's a quick quiz that kind of builds on the topic that we just talked about, which is at which points is or are the potential energy the greatest, at which points is or are the kinetic energy the greatest. So these points are labeled A, B, C, D, E, F, and G. If in the chat you could first tell me where potential energy would be the greatest. Hint for potential energy, use the lines. So let's say D is the Earth, the surface of the Earth. You can see, like, I guess, relatively how far each point would be from the surface of the Earth, if that makes sense. But see if you can answer the first question, and then I will ask for answers for the second question. Yeah, point A would have the greatest potential energy. Why not point G? Why wouldn't point G have the greatest potential energy? Yeah, A is higher, so there's more potential energy. Going back to the previous slide, potential energy is dependent on height. So as height increases, your potential energy will also increase. Okay. So D for kinetic, yes. D would be the point where there's the greatest kinetic energy if you were to picture like a ball rolling down a hill as it shows. And can somebody explain why point D would have the greatest kinetic energy? Anybody? Point D would have the greatest kinetic energy because that's where the ball is rolling the fastest. So as it travels down the slope, it's picking up speed, and as it goes back up, it's losing speed. Therefore, the point with the greatest amount of speed would be at the very, very bottom. And as you can see, velocity, you can refer to it as speed. It doesn't really matter because you're squaring it. You'll learn more about why it might matter later. But yes, so at point D, your speed is the greatest, and as this side of the equation increases, this side must also increase. Another reason, and I didn't include a slide on this, which I probably should have, is that kinetic energy and potential energy form a constant. So in any situation, you will have a certain amount of potential and a certain amount of kinetic energy. That number can be zero or a non-zero number. It'll never really be negative. But if you consider that system to be a closed system, which means that there is no external input of energy or output of energy, for example, this ball rolling down a hill, if you consider friction negligible, the ball will have a certain amount of kinetic and a certain amount of potential energy. And if you add those two values together, you'll get the total amount of energy in the system. Now, as you have a total amount, that total amount will remain constant throughout the course of the situation. So for this case, you would have a certain amount of energy, the total energy, at the top of the hill, and it would remain constant the entire time. However, what's changing is the kinetic and potential energies. So at point A, there is the most potential energy, but there's no kinetic energy because it's not moving yet. As soon as it starts moving, its potential energy decreases as it's going back towards the Earth, but its kinetic energy increases. And then it hits the very, very bottom where there's no potential energy because it's all the way at the Earth. However, there's all the kinetic energy. And then as it goes back up, it does the opposite. And you can kind of see that in terms of speed. So at the very top, the ball has no speed. And if the ball has no speed, kinetic energy has to be equal to 0, because if this is 0, 0 times anything is 0. And then if we go back to this, as the ball picks up speed and loses height, eventually at point D, H will be 0, and for the same reason, potential energy will be 0 there. Okay. Let's see. So does anybody have any questions on that kind of like physics tangent? Nope? Okay. Then let's talk about thermodynamics. So thermodynamics is going to be a more biological take on energy. We kind of just did like the physics take on energy. This will be a more biological take on energy, but you will study this a lot in chemistry. So in biology, you might spend like half a unit on this. In chemistry, it's a whole unit in of itself, and you'll go into it in a lot more depth. Okay. So what is thermodynamics? Thermodynamics is a study of the relations between heat and other forms of energy. It is focused on rules that govern all energy exchange, and though mathematical calculations are used, conceptual understanding is necessary. So thermodynamics is very math heavy. However, today I will show you a few equations, but we really won't do too much math. You'll be doing a lot of math in your homework, but you can't do the math without understanding the concepts behind the math. And so that's what we'll be talking about today. Oh, sorry. I want to give you guys a heads up. You can use more difficult math concepts like logarithms and stuff and apply it to thermodynamics. However, it is very chemistry heavy. So if you haven't learned that material yet, there's no point in me explaining it to you because it's not biochemistry, it's like strictly chemistry. So the equations you're going to use and the variables you're going to use are going to be like very basic mathematics. I think the hardest thing you'll have to do is multiply and use negative numbers. So you should be okay. Okay, so the first law of thermodynamics states that energy cannot be created nor destroyed, it can simply be transformed. So it actually doesn't say that. It says something a little bit more complicated and difficult, but this is kind of the general gist of it. And this is what the important takeaway is. You can never create nor destroy energy. There is no like infinite energy. We have a finite amount of energy in our system, but we're not using it. We're not depleting it because we're just transforming it. So if you look at this image right here, it depicts a scale. You have a certain amount of energy before a reaction occurs. You will have that same amount of energy after. Whether that energy is dispersed through the universe or it's converted from heat energy to light energy or electrical energy to light energy, it's just converted. It's never destroyed or created. Okay. The second law of thermodynamics states that the total entropy will never decrease. It might stay the same. It might stay the same for a reversible process or increase for an irreversible process. So there are quite a few words in here that you might not know. First off, let's start with entropy. Entropy is a measure of disorder in our universe. It is a form of energy that exists all around us. It's kind of an abstract concept, but it's a measure of energy in the universe. So total that total energy will never decrease. That's kind of taken from the first law of thermodynamics. However, our universe favors disorder, and that's probably really one of the most important takeaways from this. Our universe favors disorder, which is why if you have a process and it is reversible, such as this situation right here where you melt ice into water, then total entropy can stay the same. The reason for that is a block of ice, if you picture all the molecules, they're tightly packed together. That is not as disordered as a puddle of water, where all the molecules are more spread out and they move a lot more freely. So a puddle of water is more disorderly, and for that reason, it is more favorable. However, this process is reversible because just as you can melt ice into water, you can freeze water into ice. When you melt the ice and form water, you are increasing entropy. You can see delta S increases, that's the change in entropy. And when you freeze water to form ice, delta S decreases. So the change in entropy is smaller. It's losing entropy. That was not really a correct way of phrasing it, but I think you get what I mean. So as for an irreversible process, this is why delta S cannot stay the same, is because if you were to melt a block of ice and it was just impossible to refreeze the ice, think about something like, this is kind of hard to think about. Oh, something like if you pop corn. So when you pop corn, you can't unpop it, right? Popcorn can never be turned back into the kernel. So that's kind of like an irreversible process, and that would increase delta S. Because you can't go back the other way, delta S could never stay the same. Okay, I'm gonna keep going. So here are some symbols to know. First up, we have the delta symbol. Delta means a change in. So we just use it as delta S. Delta S is the change in entropy. Delta will be applied in front of most of these symbols to show a change in, but I didn't bother putting it in front of every symbol because that's just a waste when I could tell you what delta means. Okay, so P stands for two things. One, it stands for potential energy, but usually you'd write PE, or it can stand for pressure. So pressure won't be really relevant in this situation. However, you might see it a lot in chemistry. So really quick, we'll just discuss. Pressure is like obviously the amount of pressure in a system. Let's say you had let's say you had a gas and it was in a box. And you had a certain amount of that gas in a certain sized box, let's say a 4-liter box. And you were to compress the 4-liter box into 2 liters. That gas would become more pressurized and it would be forced to take up less space, because while there is a constant amount of that gas, there's less space for it to occupy. Therefore, the pressure would increase. It's kind of like a really simple rundown on what pressure is. There's a lot of calculations involved in it, but I think you kind of get what I mean. Then we have kinetic energy, which is modeled by K, but usually you write KE. W stands for work. That's very much a physics topic, so we're not going to talk much about that. So now we have Q. Q is a chemical symbol, and it stands for reaction quotient. Reaction quotient. It shows the ratio of product to reactants. So let's say you were mixing, you were taking oxygen molecules and mixing them with hydrogen, O2 gas, so oxygen molecules, and you were mixing it with H2 gas to form water. If you did that, you would have O2 and H2 as your reactants, and you would have H2O as your product. So the reaction quotient basically takes those values and it determines how much of those values or how much of those substances you have. It'll divide them and it gives you a number. That number is used in a lot of thermodynamic calculations. And I mentioned earlier that you could use logarithms to you could use logarithms in thermodynamics, but I wouldn't make you. So when you're taking chemistry, you're going to use logarithms and this letter Q in your thermodynamic calculations. However, in biology, you don't need to do that. You just, because you're not analyzing reactants and products, you use a few other variables. Okay, so S, we already know stands for entropy. H is enthalpy. Does anybody know what enthalpy is? Does anybody have any guesses at what enthalpy is? Total heat, exactly. Enthalpy is total heat in a system, and as soon as we put a delta in front of it, it means the change in total heat of a system. Then we have G, which is Gibbs free energy. G is kind of like an arbitrary number. It doesn't really mean, or arbitrary variable, it doesn't really mean anything. But just as we have that equation, I'm going to go back a couple slides. Just as we have that equation here, KE equals this amount. So KE is arbitrary like that. G would be the same thing. It's basically what appears at the other end of the Gibbs free energy equation. And then T is temperature, and I put K in parentheses because K is the abbreviation for Kelvin, which is a unit of, I guess, temperature measurement. So just as you have Fahrenheit and Celsius, you will use Kelvin. So I don't believe, I'm trying to think back. In AP Biology, you might be introduced to Kelvin, and the conversion between Celsius and Kelvin is very, very easy. You just add, I think it's 273 or something, I think it's 273. And yeah, okay. And then in chemistry, you will definitely be using Kelvin like all the time. But yeah, okay. So I think that's everything on this slide. Or was there anything I wanted to talk about? No, I don't think so. Okay. So here we have Gibbs free energy. Gibbs free energy is very, very important because it gives you a lot of information about the energy in a system and the energy following a reaction. Yeah, okay. So Gibbs free energy gives the energy associated with some chemical reaction. It's basically, it tells you the available energy. So that's kind of what G, the variable, is. Gibbs free energy can be used to determine the spontaneity of a reaction, which we'll talk about a little bit more. And as I mentioned earlier, there's two equations you can use. You will generally use the first equation in biology and the second equation in chemistry. The first equation you use in biology because you don't know what Q is. You never would have learned it. However, in chemistry, you do know what Q is. You learn about Q first, and then you apply it to thermodynamics. However, you will also use this in chemistry. Okay. On your homework, you will use this equation to solve a couple problems. But yeah. So here's a continuation on Gibbs free energy. So basically, the value of delta G is the important part. It's what gives us all the information that we need. If delta G is positive, then the reaction, it means the reaction accepted energy from outside of the system and was non-spontaneous or endothermic. Okay, so I told you already that the universe favors disorder. Disorder occurs when you release energy into the universe, into the system. It's the breaking of a bond or the melting of water, stuff like that. The universe wants like gas. It doesn't want solid substances. So let's see. Oh, just a really quick example of this is that if you had gas oh my God. If you had a gas compact in a tank, like nitrogen gas, and you were to say, hey, gas, move into this bigger tank, the gas would spread out in the tank. That's kind of an example of how the universe favors disorder. It favors more spacious arrangements and less like confinement. Okay, so just as the universe favors disorder, it also favors spontaneous reactions. So anything that can occur without an input of energy is a spontaneous reaction. It's anything that that can just occur on its own. So reactions that are spontaneous are generally exothermic. They release energy into the system, and this all ties together because the universe favors disorder, so it favors exothermic reactions which release energy into the system. And because the universe favors disorder, it doesn't require energy to carry out spontaneous reactions. So they kind of all tie together, they kind of all mean the same thing, but they're different ways of describing it and analyzing it. It's like looking through a different lens each time. So if delta G is positive, then the reaction was non-spontaneous. It means it required a net input of energy. And if delta G is negative, it was spontaneous. It released energy into the system. Okay. So the variables we have here, delta G is kind of like the end value. T is the temperature in Kelvin, always in Kelvin. Delta S is the change in entropy in the system, which will usually be a value given to you. And same with delta H, which is a change in enthalpy. And I think that's all. Okay. Oh, I'm pretty sure I mentioned this on a later slide, but energy is usually measured in a variable called joules. Yeah, I do talk about it a little bit later, but energy is measured in a variable using a unit of measurement called joules. It's, if you've heard like calories, it's similar to calories. But yeah, joules measure energy, and it is not spelled as you think it would be spelled, but it's spelled not like what you're thinking of, I can guarantee it. Okay, so energy reactions. This is like a chemistry intensive version of it. So here we have biochemical reactions, which often result in the creation or breaking down of molecules through the formation or destruction of bonds, respectively. So basically, if you create a molecule, you're usually forming a bond, and if you break down a molecule, you're usually destroying a bond. The primary example I can give you would be the breakdown of, or the transformation of ATP to ADP. It is a reaction that breaks the bond between the P and the O atom. So yeah, bonds store a lot of energy, so forming them requires an input of energy, and breaking them will release that energy. Let's see, there are various circumstances that can change the amount of energy required for a reaction. So I'll talk about these circumstances in a little bit, but it's often things that are like super mundane that you wouldn't think about, but stuff like temperature or pH or light can alter the amount of energy that you need for a reaction. For example, great example, actually, looking back at this equation, if you're in an area with a really high temperature, then it is going to take a lot more, if you're in an area with a really low temperature, it would take a lot more heat, like input of heat, to melt the object. Yeah. Okay, let's go back. And then the last bullet point is generally those reactions that release energy are favored in the universe as they increase the entropy or disorder, which we talked about. Okay, so here are some terms that you need to know. So joules, which are the unit of measurement for energy, and they're abbreviated with a J. Activation energy, which is the minimum amount of energy required to even begin a reaction, and it often depends on external conditions. Catalysts, which are enzymes or proteins that can help a reaction proceed and often reduce the activation energy. Endothermic is a reaction that requires energy from outside the system, and exothermic releases energy into the universe. Okay. So here we have an image of an endothermic reaction and an exothermic reaction. I'm not really sure what these graphs are called, but I usually call them like energy graphs. So on the x-axis, you have the direction of the reaction. That basically just means, I guess you can think of it as like time that's passed, but usually it'll show the reaction itself right in the middle. It'll show the energy level before the reaction and then after the reaction. So as you can see, we have stored chemical energy on the y-axis, so that would be pretty intuitive. So for an endothermic reaction, we know that it requires energy from the outside. So your reactants will have a certain amount of energy within them, and then they will require, this amount of energy to undergo the reaction, and the products will end up with more energy than before. The way you can think about this is if you have two separate molecules and then they're joining together, so you're basically forming a bond, you know that breaking a bond releases energy and forming a bond takes in energy. So it would be intuitive to think of your products being like the complete molecule as having more energy because of that bond. So that's exactly what's happening. Your reactants have less energy and then the products have more energy. Exothermic reactions are the exact opposite, where you release energy. Your reactants have more energy. So think of like a final molecule, and then you break that bond, creating the products, which have less energy because you've released that energy into the system. So this is the kind of graph that I will ask you to draw on your homework. And basically it's the exact same X and Y axis as before, but you have your stored energy, your potential energy, and then you have like the progress of the reaction. So in this case right here, we have our, a lot of labels here. So you start off with your reactants, which have little potential energy, and then you go all the way up. And if you see right here where it's labeled transition state, and then you see where it's labeled products, you actually go above the products. So if we go back a slide, this doesn't really show that, but you will always have to have more energy than you started with, if that makes sense. So even in an exothermic reaction where you're releasing energy, your curve would look something like this. You would have your reactants that start, you can't really see that, hold on. You would have your reactants that start, and then you would absorb some energy, but then you would release that energy and more to form your product. So this would be like the difference in energy. This would be what's released. Okay, but back to the image at hand. This right here shows an endothermic reaction in which energy is absorbed. So your reactants start low. Then you have this E-act. This E-act is your activation energy. It's basically like the energy that you need just to do the reaction, like carry out the reaction. So the activation energy will go all the way up, and then it'll drop a little bit and you'll have your products. This net change marked by delta H would be the energy absorbed in the endothermic reaction. So this is very, very intuitive and straightforward because you'll start at the bottom and you'll go all the way up. So this is all the energy that you absorbed. Then you'll release some of that when you make the products and you'll be left with this net change. Okay. So do you guys have any questions overall? I'll give you guys like a minute to see.